In the last video, we took a look at some special right triangles and introduced this idea of looking at certain ratios in those triangles. We looked at the opposite over the hypotenuse, which we referred to as our sine. We looked at the adjacent over the hypotenuse, which we referred to as our cosine, and we looked at the opposite over the adjacent, which we referred to as our tangent. But we only looked at it with two specific triangles, the 30-60-90 and the 45-45-90. This question here says, do you think this would happen in other right triangles, or will this only happen in the special right triangles we studied? So take a moment and think about that. Maybe pause the video. Okay, I'm assuming you had a chance to think about that. And, would this happen in other right triangles? The answer is going to be yes. So no matter, let's draw a random right triangle here. So draw my best right triangle here. And let me get rid of that top piece. Okay, now I'm not going to measure this, but let's just say that the triangle that I just drew here, let's say that this was, I don't know, let's say this was 25 degrees. And so this is 90 plus 25, that's 115. So I know that up here, to have my 180 degrees in my triangle, that has to be 65. So 65 and 25, that would be 90, plus this 90 is 180. And in this triangle, I have certain lengths here. I don't know what this is, but this is some length. We'll call it X. Across from this 65 is some length. We'll call it Y. And across from this is some length. We'll call that Z. And we don't know exactly what these are, but we do know the ratio of them. So if you type in, for example, the sine of 25 degrees and get what that is in decimal form. So actually here, let me take a moment and do that. So let's see what the sine of 25 is. Let me clear my calculator here real quick. And so I have sine of 25, and it's 0.42. If I round this, it'd be 0.423. So the sine of 25 is about 0.423. So what that means is I know that sine is the ratio of my opposite, which is x, over my hypotenuse, which is z. And although at the moment I don't know what exactly x and z are, I do know that whenever I take this length divided by this length, I'm going to get about 0.423. And the reason that this works is because every one of these triangles, these 25, 65, 90 triangles, they're similar triangles. Similarity happens anytime you have a pair of congruent angles in your triangles that you're looking at. And every 25, 65, 90, no matter how big or small I draw it, those triangles are similar to each other. And because of that similarity, these ratios are always going to stay the same. So the foundation of trigonometry is the observation that all right triangles with a given acute angle are similar by the angle-angle similarity theorem. For the triangles shown below, this means that the ratios of, and let's see here if I can pull this up a little. Let me resize this real quick. Okay, so a little bit smaller, but now we can at least see the whole picture. So if I look at my ratio of AB to BC, notice this is 28 degrees here. That is going to be the same as this ratio of JK to LK. Even though this is a different size triangles, when I divide these two values, I'm going to get the same number every single time. And that's going to be the same as the ratio of PQ to RQ. Thus, given a 20-degree angle in a right triangle, the ratio of the length of the leg opposite the angle to the length of the side adjacent to the angle is well defined. That is, the ratio does not depend upon the size of the triangle. This ratio is defined to be the tangent of 28 degrees, written tangent of 28. And if you remember from a little bit ago, we talked about how your tangent of an angle so we'll say tangent of angle A is always your opposite side divided by your adjacent side. And that is exactly what we looked at. So with respect to this 28, we looked at the side that's opposite that, which is AB, my opposite side, over my adjacent side, which is BC.